In this video, we're going to look at mathematical induction. So here's a brief definition of it. Mathematical induction is a method for proving that statements involving natural numbers are true for all natural numbers. And of course, the natural numbers are 1, 2, 3, 4, and so on. There's several types of proofs that you can use in mathematics, especially advanced mathematics, direct proof, indirect proof, proof by contradiction. This particular one is used when the statements involved are strictly natural numbers. So let's look at the theorem. The principle of mathematical induction supposes that the following two conditions are satisfied with regard to a statement about natural numbers. So here are the conditions. Condition 1, the statement is true for n equal 1. And you can test that right away. You test it for n equal 1, see if it works. Okay, that satisfies the first condition. And then the second condition, if the statement is true for some natural number k. So you test it out for some number k, natural number k. It is also true for the next natural number, k plus 1. So it says if the statement is true for some natural number k, it is also true for the next natural number, k plus 1. So you make that assumption that it's true for some natural number k. And then if you can show that it's also true for the next natural number, then we can conclude that the statement is true for all natural numbers. So for the first one, it says use mathematical induction to prove that the sum of the first n natural numbers is given by this formula. So for the first step, we want to show that it works for n equal 1. That is the first number in this sequence here. So let's put a 1 right there where the n is. That's 1 over 2. And then 1 and 1 is 2. We get 1. And you can test it for others. So this one checks. But notice, I can test it out for the first 4. Let's suppose we want to test it out for n equal 4. We don't have to do that, but just to show you. For the first 4, let's just set them up. So 4, 3, 7, and 3 more, that's 10. And put the 4 over here, 4 there, over 2 is 2. This is 4 and 1 is 5. 2 times 5 is 10. And you can keep on going. You can say, well, sure, it's true. It works. It keeps working. But to get credit, you have to use the principle of mathematical induction. So anyway, we showed it for the first case. So it's true for n equal 1. And then we assume that it's true for some integer k. So in other words, we have 1 plus 2 plus 3 plus 4 plus ... It continues plus k. So we assume that this is true. So notice it's the same thing, except instead of n, I'm putting down a k. So this has to equal to k over 2 times k plus 1. So now I have to show that if I add plus k plus 1, then in other words, the next one, it's going to also work. So this, in other words, it's just going to be 1 plus 2 plus 3 plus 4 plus k, and then k plus 1. So we're assuming it works for the first k, and want to show that if you make that assumption, that it's also going to be true if you go to k plus 1. So we're looking at this right here. You look at this right here then. We use that information, so we know then that for the first k, it's k over 2 times k plus 1. So all I did here is I took the first k values here, 1 through k, and we're assuming that's equal to, based on the formula, k over 2 times k plus 1. Now what happens if we add the next one here? It's over here, and now we're going to add it over here, plus k plus 1. So what we have to do now is we have to show that it gives you this exact same formula, except where you have a k, it's k plus 1. So I'm going to go up here, and we're going to combine this out. So I'm going to multiply this one by 2 here, and 2 up here. They have the same denominator, and it'll combine that. So it'll be 2 here, and then it'll be k squared plus k squared there, plus k, and over here multiply through by 2, so this will be plus 2k. plus 2. So let's just combine here. We have k squared, and then k and 2k is plus 3k plus 2. So far we have k squared plus 3k plus 2. Now we just factor this. And this is going to factor k plus 1, k plus 2. And this is over 2. So I said that you had to get this formula right here. It had to come out to this. Except where you have a k, you have to have a k plus 1. That's what the formula states. So notice the first factor, and of course the 2's there. I put it all over 2. It's just a 2 here, but I could just draw a line there and put everything over 2. So there's k here. There's k plus 1 there. That checks out. Now this one has k plus 1, but remember, k plus 2 is the same thing as k plus 1. Plus 1. So it fits. We said wherever you have a k, if this is going to be true, you have to have a k plus 1. So there's my k plus 1 here, k here, k plus 1 here, about everything under 2, over 2, and then there's a k plus 1 there, or k plus 1. So in this case, I have k plus 2, but then the next natural number is k plus 1. So there it is, k plus 1 plus 1. That one checks. So if you're doing something by using mathematical induction, and again, that's statements involving natural numbers, you first have to show that the formula holds when n equals to 1. You can go further if you want, but that's all that's required, n equals to 1. And then you assume that the formula or the statement is true for the first k values, first k natural numbers right here. So if you assume that's true, and you can show that the formula is also true for the next natural number, which would be, in this case, the k plus 1, then you can conclude that the statement involving natural numbers, or you can call it a theorem, is true for all natural numbers. And that's the case here. Thanks for watching. We'll see you next time.